great to see so many people interested in the Tasmanides. And I'm a bit out of my comfort zone here because I'm not an economic geologist. I'm working on tectonics and structural geology. But I'm interested in why ore deposits occur where they are. And I show here, right at the beginning of the presentation, a comparison with a very famous arc system in the Central Andes. Everybody is recognizing the Central Andes. We see here in red the quaternary arc and some gaps in the arc, some bends. We see the subduction zone. And at the same scale, we also see the New England. Yeah, the scale is exactly similar. The curvature of the Bolivian ore line, similar kind of curvature. And the same arc with its gaps and bends. But one of the major differences, of course, is that in the Central Andes, we have a lot of ore deposits. The ore deposits that we see here are porphyry copper deposits from the USGS database. And the same database has some information on the rest of the world, and we can see that there are some porphyry copper deposits, but they are much more scarce. So what is the reason for that? You know, what makes the New England different from the Andes? So the New England is it's the easternmost part of the Tasmanides, the youngest component of the Tasmanides, with deformation, particularly during the Permo-Triassic, the Hunter-Bowen orogeny. So a system that evolved mainly during the Devonian and Carboniferous and was subjected to deformation and magmatism during the Permo-Triassic. It's been described as an Andean type system lying on the continental margin of eastern Gondwana and subjected to a long period of subduction processes, arc magmatism. Yeah, similar to the Andes. Yeah, the Andes been situated in the same kind of position in western Gondwana for a long while, and as I mentioned before, very rich in porphyry deposits, again from the USGS database, 139 copper porphyry deposits, an enormous amount of contained metals, and a comparison to the New England, you know, just 10 copper porphyry deposits in the same database. So I'd like to start with a little bit of an overview of, you know, from my kind of from the tectonic kind of point of view, what makes fertile arcs. And there are a number of kind of interesting ideas in the literature, mainly influenced by the information we get in the Andes. So an idea put forward by Kay and Podozis some 25 years ago is about the relationship between porphyry mineralization and flat slab subduction, with the idea that due to the release of fluids from amphibole-bearing crustal assemblages, mineralization occurs particularly during flat slab subduction, when the slab is flattening, and particularly at the very end of the flat slab period. So it has a few implications, because flat slab subduction would be directly linked to orogeny. Yeah, it's a period that has more coupling between the downgoing plate and the overriding plate. So there we expect to see pulses so the pulses of mineralization events are kind of simultaneous to a thrusting and folding and crustal thickening. So that's one thing. The other thing is that flat slab subduction would lead to a migration of the arc. The arc is gradually migrating landwards, so arc advanced. And again, there in different locations, not only in the Andes, we see that there is some kind of relationships between clusters of ore deposits that are occurring when the arc is advancing, and also when this arc advance is kind of culminating in a magmatic flare-up. So we get kind of magmatism, rhyolitic magmatism covering a pretty large area and much more voluminous. And at the end of that flare-up, the arc is kind of shut down. The flat slab subduction is terminating the arc activity, so we get those volcanic cycles. Okay, so all deposits have been described in associations with all these kind of different features. And the other things could be related to that is the relationship with the material that arrives from the downgoing plate. So here's an exercise that I did already quite a lot of time, quite long time ago, and it shows the effect of those anomalous ridges at the overriding plate of the Nazca plate, and whether they are kind of empirically linked to the distribution of ore deposits in the Andes. So I reconstructed the position and the shape of the Nazca Ridge based on all sorts of different arguments from the other side of the Pacific Ocean. And here we see the tip of the Nazca Ridge here, arriving at the subduction zone in Peru. And there's another ridge here, the Inca Plateau. It's been already consumed by the subduction zone. And the moment that the Nazca Ridge arrives at the subduction zone, we find a large cluster of ore deposits exactly opposite the ridge subduction. So perhaps the dynamics of the system is changing due to the arrival of this of the ridge subduction. Perhaps material from the ridge contributes to mineralization. Here, the overall kind of kinematics here is a kind of a oblique plate velocities relative to the boundary. Therefore, the Nazca Ridge is gradually migrating southward, and we can see that in general the ore deposits are migrating together with the ridge. So interesting kind of relationships. Maybe the arrival of the ridge is tearing the slab apart because the ridge is more buoyant. An idea that we tested in other localities. Jack Ward is here in the audience, and as part of his PhD project, he looked at the Sunda arc, and we can see that here is a seismic tomography layer at 335 kilometers. We can see that there are gaps in the slab, and it is exactly where those gaps are occurring where we find large ore deposits in Indonesia. So the other thing that we find in the Andes, for example, is that maybe the system is already kind of fertile. It's been fertile all the time. So ore deposits are just reoccurring. Perhaps that's the reason that immediately when the ridge is arriving at the subduction zone, all those minerals that are already there, all those elements are reoccurring. So just a recent paper by Silito showing that many of those Meissen ore deposits are actually reoccurring at the same place that they already were before. Okay, so moving to the New England, what I'd like to do is to summarize the simple plate tectonics of the New England, then showing a number of problems, so major problems in the plate tectonics of the New England, and then try to link that to the occurrence of ore deposits. So let's start with a simple story. The simple story is that the New England origin mainly comprises Devonian Carboniferous arc, 4-arc system. That is one of the major components of the New England. We can see here on the map. And the 4-arc system, as Ross said before, comprises of 4-arc basins sitting on top of an accretionary complex, and here is the arc. And a lot of the material that we find in the New England origin it belongs to this late Devonian to Carboniferous arc system. So that's a pretty simple kind of plate tectonic configuration. Then we have a whole kind of story of early Permian basins and granitoids. And in those basins, we can see them here. It's the Bourne Basin would be part of that system. All those basins here, the Mbaka basins, and basins here in the Queensland part. They are associated with extensional structures. They form the overriding plate in a back arc system. So moving from the Carboniferous to the Permian, we're moving from a system that was in a forarc to a system that was then in a back arc. We interpreted some of those granites as back arc related granites that basically form by crustal melting in a hot back arc system. So an extensive back arc region. And then moving to the late Permian and Triassic, this is also when the Hunter-Bowen orogeny occurs. We are back in the arc system. So there is kind of a mobility of the plate boundary. Here we see a lot of granitoids and also arc volcanic rocks. And you know, in a kind of a plate tectonic scheme, you know, perhaps we're in a kind of Chilean Andean type subduction boundary with you know, right at the heart of the arc system. Okay, so a pretty simple plate tectonic history. We are in the Carboniferous here, in a forarc region. The subduction zone is retreating during the early Permian. So the same system is now in extension. Some of those accretionary complexes are molten by in the hot back arc region, forming the S-type granitoids, and then again advance perhaps of the subduction zone and flattening of the slab during the late Permian and Triassic. So there are a lot of problems here. The system is obviously more complex. So what are the problems? The first one that really I kept scratching my head, what is going on, is that the boundary between the forarc basin, the accretionary complex during the late Devonian and Carboniferous is not an unconformity, an angular unconformity as one would expect in a normal forarc region. What instead we find is a tectonic contact, and so these are the Yarrow Fault, the Peel Fault, and the Manning Fault. And it seems that basically the whole system kind of got restructured. So along those tectonic contacts, the former forarc region got kind of had some, you know, kinematics and some a whole lot of tectonic story. And indeed, at the proximity of that tectonic contacts, the Yarrow Fault, Peel Fault, and Manning Fault, we find a bunch of older terrains. And some of them are really old. The Marlborough, for example, an ultramafic massif with some high-grade metamorphics, is the oldest occurrence, the oldest rocks that occur in the whole of the Tasmanides, older than the rocks in the Delamerian origin. So we find Neoproterozoic rocks here in Marlborough. We find Cambrian rocks here along the Peel Fault. So we find ultramafic massifs, and we find island arc terrains. Again, they are not, maybe not exactly along, like within those within those tectonic contacts, but they are in the general proximity. So island arc rocks that they collectively called the Gamila Roy, Silverwood in southeast Queensland, and the Calliope terrains in central Queensland. So what is the origin of those older terrains? Early Devonian terrains, some Silurian rocks, even Ordovician. And finally, why is the entire orogeny is contorted? We already see from the kind of those maps that I created here that the whole system is strongly contorted in the same way that Ross described the Lachlan orogen. If we follow those ultramafic belts from Port Macquarie to the Manning Basin, Peel Fault, and the Bayougal here, follow the aeromagnetic kind of imaging of that, we can see very, very strong kind of curvatures, and all the way to the Yarrow Fault, Marlborough, and Percy Islands, perhaps. And then we find the same kind of curvatures if we follow the Fork Basin terrains, if we follow the accretionary complex terrains, and even when we look at the early Permian granites, particularly in the southern New England origin, we can see that they kind of mimic those contorted structures. So, what is the reason for that? Obviously, the plate tectonic history is more complex. So, moving to the mineral deposits, for the sake of this presentation today, what I decided to do is to try to think about links between what we know and what we think we know about the plate tectonics and the mineral occurrence, the ore deposits in the New England origin. So I looked at the Australian Mine Atlas, and those are the mineral deposits, historic mines, operating mines that we see here in the large circles, and the small circles are mineral occurrences. And we can see that there are a lot of metals, a lot of gold and copper, silver, and others. And what I basically did is try to kind of scrutinize each one of those mineral deposits and put that in a tectonic context. For some of them, I have better idea. For some of them, I had no idea at all, and I left them. Some of them would not appear here because I had no clue what they're related to. So, starting with those older terrains, with the ultramafic belts that I mentioned before, there are quite a large number of ore deposits and mineral occurrences that are directly linked to that ultramafic belt. So we can see occurrences in Port Macquarie, in Bayougill, Kilkivan, and around Rockhampton and Marlborough, directly linked to the occurrence of ultramafic rocks in that belt. So these are particularly cobalt and nickel, chromium, PGEs, and also gold that are hosted by the ultramafic rocks. Perhaps there is some sort of continuation to that undercover, so an interesting kind of interesting idea from the exploration point of view. From a tectonic perspective, I'm really interested to understand what actually this belt indicates. Is it a dismembered ophiolite? Is it a continuous belt that goes all the way from Port Macquarie to Percy Islands? And what are the tectonic implications? Is this kind of some sort of lost ocean of Eastern Australia that represent a suture? So it has huge implications to understanding the plate tectonics of the New England. So we're working on that in an air-sea linkage project with the Geological Surveys of Queensland and New South Wales, and we have a poster here by Julius, one of the PhD students working on that, so take a look at that. Moving to the Devonian Carboniferous arc system. So a very long history of subduction, maybe 80 million years of subduction, but as you can see here, very little, a very small number of deposits. The only one that is reasonably large is Mount Morgan, a bit older, late Middle Devonian deposits, and we don't really see any porphyry deposits. So most of these deposits are orogenic. So what could be the reason for that? Perhaps I could think about two reasons. Either the arc is not preserved, or the arc is barren. So if we think about Queensland, this arc is mostly eroded. We don't really see much of the arc here. And in New South Wales, the arc is mostly covered by the Gunnedah-Sydney Basin. So, one possibility that we have all those porphyry deposits under the sediments of the Gunnedah Basin. More likely, it's a barren arc because probably if it was more fertile, would have some vectors towards it. Moving to the early Permian deposits, we can see that the early Permian deposits, because it's an extensional environment, is dominated by epithermal gold. So kind of a belt of epithermal deposits. The most sizable one is Cracow Golden Plateau. Some deposits here in New South Wales as well. And if we think about the plate tectonic context, that could be directly linked to the development of those curvatures of the oroclines. So, you know, I don't know exactly what's the plate tectonic plate tectonic origin of those oroclines, but in all the reconstructions that we did, we tried to kind of think about the effect of subduction rollback and the rotations of blocks to form the oroclines. So, you know, if you put that in the context of this epithermal belt, you know, perhaps it's part of a rollback story. We have a kind of extended back arc here, and you know, the hyperextended arc in the Gympie province here. Moving to the early Triassic deposits, one thing that is striking here is that almost all those ages are the same. They are around 250 million years. So something is going on around 250. We have a porphyry copper moly belt here in Queensland. We have some sizable deposits in New South Wales. And to understand what could have happened at 250, we might want to look at the geodynamics of the Hunter-Bourne orogeny. When did the Hunter-Bourne orogeny start? Around 270. This is Chris Fielding here sitting just in the transition between the kind of must-wasting sedimentary deposits of the early Permian that started to see the kind of fall and loading of the rising topography. So, you know, using that, we're able to say that the Hunter-Bourne orogeny started at 270. It was accompanied by arc magmatism, and we see that we have peak magmatism at 250 when all these deposits happen. Yeah, in the northern New England origin, we see that also in the southern New England origin, essentially a magmatic flare-up at 250. And importantly, we see arc advance. So if we look at the arc here, if we map the arc, we see that there's arc advance, and our interpretation of that is that this is the effect of flattening of the slab, so kind of local flattening of the slab. So we see the ingredients here that we also saw in the Andes. You have flat slab segments coinciding with the copper moly deposits. Okay, here is a kind of a longer, a larger scale picture of that, showing this kind of curvature in the whole of the Tasmanides. And if we compare that to the thickness of the overriding lithosphere, this is from seismic tomography, we can see that there is a thicker kind of lithosphere exactly at the area where we get this kind of pinning. Okay, so that is the thicker lithosphere, and the bending and the flattening of the slab could be directly related to that. And finally, the late Triassic deposits. You can see that we see some, again, there's a kind of there's a cluster of all deposits at a pretty short period, 235, 230, some porphyry, intrusion-related orogenic deposits, and importantly, it is the final stage of the Hunter-Bourne orogeny at 230 when we get these kind of clusters of ore deposits, yeah, both in the northern New England origin and the southern New England origin. Okay, so to conclude, unfortunately, the Andean-type New England origin does not seem to host many Andean-type porphyry deposits. That's bad news, I'm sorry. And, you know, ideas that are maybe the crust is too thin, no inherited fertility as we see in the Andes, but we still can get some information from plate tectonics on mineral provinces, and there are mineral provinces in the New England. The ultramafic belt with you know, nickel, cobalt, chromium, PGE, and gold, the early Permian epithermal belt, the 250 million year intrusion-related belt, and the final stage of the Hunter-Bourne. Thanks a lot.